So I'm going to present a logical framework and to try to capture some aspects of the behavior of quantum measurements. The idea is that basically all you know from quantum system is obtained through measurement outcomes. And so if you formalize this a bit and you study the models, it might teach a few things about how to define the state of the quantum system or something like that. So basically I will first define my logic and then talk a bit about models, and I will show a few, I think, interesting results about that. So I'm sorry, it's quite an old-fashioned logic, no categories, no diagrams, as you'll see. So I have a basic term, basic constructor, which looks like that. So what does it mean? It means that a quantum system, labeled by S, has been measured with observable O, and it yields output P, and T denotes the obtained system. Okay, so first only sharp observables, and basically the outcomes we will see them as elements of an orthomodular lattice, even though rather quickly we will turn to Hilbert space subspaces. So here are a few interesting axioms to start with. So the first one, what does it tell you, is that the bottom element of your lattice, the null subspace, cannot be a valid outcome when you measure a system. Okay. Moreover, this bottom element is the only element of your lattice which cannot be obtained as an outcome. Any other element, well, is, can be obtained as an outcome. And finally, what does this axiom say? It says that whichever system you measure with whichever observable, you will obtain an outcome, like a resulting system. Okay, it's first kind measurement. Okay, this is three basic axioms just to modelize the notion of outcome. So to make things a bit more readable, let's have some syntactic sugar. So this means that P verifies, S verifies P, sorry, and what it does mean is that when you measure S, you cannot obtain P orthogonal as an outcome, okay? So the previous three axioms, oh yeah. So basically in a Hilbert space, if S is in the state P, saying that S verifies P corresponds to having phi an element of P. Okay, it's just P is then a subspace and phi is an element of P. So the previous axioms now can be read this way, and which means that S verifies the top element. It does not verify the bottom element, and okay, any element different from the bottom element can be verified, is verified by some system. It's just a translation of the previous things. Okay, so that's just the basic axioms. Now we're going to add two more important things. First, it's what I call weak non-contextuality. It's just the observation that when you measure a system, basically the prediction you can make about the certainty of the impossibility of an outcome is independent of which observable you actually measure. Okay, if you can predict that an outcome is certain for one observable, it's certain for any observable which has the given outcome as a possible one. Okay. So again, if you consider the bound rule, is just that the probability of obtaining an outcome P is independent of the measured observable. So if it's 1 independently of which observable you measure. If it's 0, it's the same. Okay. From this observation, we can derive two interesting axioms. First, if S verifies P and P is larger than Q, then S verifies Q. The proof is rather simple. You consider, okay, so this observable, if P larger than this, P is smaller than Q, this is a correct observable. And so you suppose that P is a certain outcome, so that as a consequence, this one is impossible and this one is impossible. Okay, that's with my agnostic strategy. It's very clear. So Q orthogonal here, you find it also in this observable, which has only two outcomes, Q and Q orthogonal. And so if Q orthogonal is not possible, this entails that Q is certain. Okay, so if S verifies P, then S verifies Q. Okay, another one is this one. If you have two compatible outcomes, P and Q, and if S verifies both, then it verifies their meet. Again, let's consider those three observables. So first, P is certain, so you cross out those outcomes, and you also cross out the corresponding outcomes in the third observable. Now, Q is also assumed to be certain, so this one is impossible, and this one is impossible too, so P and Q is the only one remaining. So, okay, you deduce from this and this that P and Q is also certain for S, that S verifies P and Q. Okay? And the final basic rule I want to use is the following one. If P and Q are compatible, if S verifies P and if S has been measured with outcome Q, Q being compatible with P, then the obtained system T is also verifying P. Basically, so this states that when you measure S, you cannot obtain anything orthogonal to P. And if S has been measured yielding system T with output Q, then this kind of verification statement still holds. That means, again, if you measure T, you cannot obtain anything orthogonal to P. This is very easy to justify using projectors. Okay, so to a final definition. So it's very typical to orthogonal lattices. This is a classical projection of A on B, and it's defined this way. Basically, in Hilbert spaces, it corresponds to an orthogonal projection on subspace. Okay, just like a theoretic equivalent. So it allows us to drop the compatibility requirement in the previous axioms. And so, for instance, what we've just seen, so we drop the fact that P and Q have to be compatible, and so if S verifies P and S is measured yielding outcome Q, then the resulting system T verifies P projected on Q. Okay, so it's just something which is very easy to deduce from the previous things. So, to sum things up, here are the few axioms which are used to define my logic. And, well, we'll see what we can say about the models of this logic. So what is a model? First, I have a little remark to do. In this slide, the only place where our basic block test appears is here. I did not write the quantifiers here, so I write them here. actually the observable O here is quantified existentially. And also the verification property also contains this nice term where the observable is also quantified universally. So basically, it always appears this way. So you don't really need to have the observable appear in your in our model. So our model will consist of two elements. First, a set which will assign some meaning, an element to each system label, and a relation which corresponds to this. Okay, so if we drop the observable, we have S and T, which are now interpreted as elements of A, and you have an element of your lattice L. So it's a relation on A times L times A. Okay? And so, terms of this form, which is now become like this, and the verification property becomes in terms of our model, something like that. Okay? Yeah.
So this triangle, we call it verification operator.
Yeah.
It's a kind of syntactic article, something.
It's just some syntactic sugar for this. I mean, okay. But it's interesting to think of things with this verification relation. Okay, so now we have our translation. So, so such a model, it's a set equal with a relation of this form. You can see this as a labeled graph, directed labeled graph. Okay, might be interesting for the future. And so such a labeled graph, so labeled by elements of our lattice, is a model of our logic if it verifies all these properties. Okay? And basically, two interesting models. First, the one I call the Hilbert model. Elements are just normalized vectors. And so you have our relation which corresponds to the fact first that if you project psi on P, you don't get the null vector, and then phi is a projected vector after normalization. Okay, so it's basically it reproduces usual projected measurements. Okay, and in that case, phi verifies P if only if, so phi belongs to P. Okay. Another interesting model is lattice 1. So this time you have an orthomodular lattice L. You consider all its elements except the bottom element, which, as we've seen, is not relevant for representing a state. And this time our relation becomes the fact that P is smaller than A projected on P. Okay, it's basically the same idea, but this time you reason with subspaces or elements of an orthomodular lattice. Okay, and then A verifies P if only if P is smaller than A. Okay, it works pretty well. Okay, so now we've defined our logic and models. And so what can we say about these models? I would like to present two theorems. First one, okay, you have a model. Given an element A, you define the set of all the elements of L if verifies. Okay. And this theorem states that if the dimension of your Hilbert space is at least 3, then A verifies at most one vector, one dimensional element. Maybe I will just sketch the proof, which is pretty fine. It's basically a topological proof. So suppose that you have okay, so that's the here you have two vectors which are assumed to be verified by A. So if A verifies, so you have phi and psi. Okay. If A verifies phi, it also verifies any subspace that contains it. Okay, so consider for instance a plane containing phi. Okay, it also verifies psi, so second rule, you can project it orthogonally on your plane and you have a new vector which is also verified by A. Okay? Yeah. If you consider that this plane turns around phi, you will have a collection of new vectors, okay, which is like that. If you look at it from above, so you have your two initial vectors and you have kind of this shape, it's like an ellipsoid. And the interesting point is that this is larger than this. So if you iterate this, you will those shapes. And after a while, it will be wide enough so as to contain two orthogonal elements. Okay, which leads to a contradiction. So you cannot have from the start two vectors verified by the same element A. Okay, so it's actually a strengthening of the Cauchy-Specker theorem. Okay, one way to describe it is that you cannot pick exactly one element in each maximum orthogonal family of vectors. Okay, and you have some proofs and dimension and the numbers of needed vectors. And what does this theorem state? That if you pick any two vectors starting from dimension 2, you will reach a contradiction. Okay, so this includes the Cauchy-Specker theorem. Okay, so that's the first interesting result on models. Another one, which I will prove here, is that in fact, so the dimension of your Hilbert space has to be at most 3, but it only works in finite dimension. For any A in A, the set of properties verified by A is actually a principal function. That means that it has the smallest element. So it strongly restricts the shape of the properties verified by A. And in particular, this means that if the dimension of H verified this, you have this rule. Previously, remember, you had the same one but with projection, and now you have a limit which is much stronger. Okay, another way to state this is that this set is isomorphic to this set. Okay, and this I think is justifies the metaphysical disaster, which was expressed was meant to mean that people in quantum logic always equate on the one hand the properties verified by a physical system, so those things, and on the other hand the experimentally testable propositions. So two things. Okay, and so in this approach I think it's unavoidable. Okay, I would like to present last result about this. Now, if you have a system and you make several measurements in a row, and the question is it possible to have a sequence of outcomes? Okay, so you have the word of elements of L, visiting the different outcomes you obtain in a row. And the question is it possible to find elements in A such that you had this, okay? This arrow corresponds to this. In terms of graphs, it means is this word labeling a path in the model. Okay, so this notion depends heavily on which model you consider at first. Well, actually, it's not the case. And because, again, if you have this constraint on the dimension, first, the language, so the set of path labels associated to those two models, the Hilbert one and the lattice one, are equal. And also, it's true for any other model of the same logic. Okay, so you have this equality. So it only depends on the Hilbert space. Okay. And so the possible sequences of outcomes is independent of which model, and in particular, they are completely characterized by using vector states in this model. Okay, so to characterization, the first one corresponds to when composing those projections, you don't obtain the new projector, and also in terms of projections, you don't lead to the bottom there. Okay. So if you forget about the specific models, you have this equality. And I think that if you consider this whole question, the answer is yes. I mean, in terms of possibility of obtaining such or such an outcome. Okay.
Are there any questions, comments? So, I'm wondering, in the sort of tradition, à la Faulis and Piron, where do you see this? Where can you sort of place this?
Aside.
Aside.
Yeah. Now, the basic idea is to try to understand what is a quantum state and what it should look like. It's more related, I think, to, for instance, ontological models. Okay, even though it's another approach because in ontological models you have basically a preparation, a measurement, and you relate both. Here, I have only one construction, a measurement, but you can have several measurements in a row.
Yes?
Yeah, so I think this is maybe just to understand sort of what this Bob was asking. So you add these new verification symbols to language.
Yeah.
Do you assume anything about the underlying logic in terms of just the normal rules of inference? Are you assuming it's what standard quantum logic, or is it standard first order logic? Does it make a difference? Do these things behave differently?
I don't think so. I mean, it's not the interesting point. Basically, I think it basically applies to sort of sequential circuits. Okay, so you have a starting quantum system, you have a first measurement, a second one, a third one, okay, and so especially the last result. So it's a very constrained setting, and it doesn't depend much on which logic you rely.
Okay.
Basically, I was rather in an intuitionistic logic approach, but I did not keep it because it was not relevant.
Okay, thanks, Pete.